So our next session is going to be on, well, if you look at the textbook, it says comparison test, but if you look at the title, I write limit comparison test because I'm going to only focus on this particular one. And so I'm skipping the actual comparison test. You can read on it in the textbook, but don't worry. It's the limit comparison test that is really important for us. But well, the word comparison means that we're going to compare it with something, right? So the question is what? And therefore, before I start, I even have to give you a quick review of what we know so far. We have seen two very important series, and they're going to play an important role here. And in fact, these are the ones that we're going to compare it with. And the two that we have is the P series. It's very important to recognize it and how it's what is going on with it. So it's something out of form 1 over np, where n goes from 1 to infinity. Of course, we have to start from 1. We cannot start from 0 here. But we could start from 2 if we want to. But all right. And so what are these? So this means that n is, if you think, you should think of n as the variable, right? So it's actually a polynomial of a fixed power p. And it's the power p that determines convergence or divergence. So we have, if p is bigger than 1, we have convergence. And in all other cases, which includes p equal to 1, we have divergence. Notice it's p itself, not the absolute value, and that's perhaps confusing because we also have the geometric series. That's the second one of importance that we're going to deal with. And so that one looks like something like this. And now we start from 0. Yeah, it's easier to start from 0 with this one. And so now if you think of n as the variable, right, I said n is a variable, then what you get here is actually r is a fixed number. And so we get a fixed number to the power a variable, that is an exponential function. So this is an exponential function in terms of n. Okay, just point that out to you. But what matters for us here is now the criterion. If the absolute value of r is less than 1, be careful, it's now less than 1, that implies convergence. In all other cases, we have divergence. So I should write it here. Okay, so, and then we have here divergence. So these are extremely easy tests. Once we know r in the geometric series or p in the p series, we know exactly what's going on. All right. So just two examples of these things here. For instance, if we would have something like that, sum 1 over 2 to the power n, what are we dealing with here? I'll let you think about it. You might say, oh, it looks like this one, but the denominators look like a p series. Huh? No, it's not that. Notice the n is the exponent here, so we are dealing with a geometric series. Now, what's the r then? Well, we have to write it in this form, so that's how we do this. And so here we see that r is a half, and we fall into the convergence case, right? The absolute value of r is therefore less than 1, so we get convergence. Okay? So I'm saying we also, this one might also not look what we want it to be. Like, what is this one? Well, you say, oh, it's a polynomial, so p is -3. No, remember, it has to be written in this shape. In other words, with the power in the bottom, which is unusual, but for this particular case, it makes sense. Okay, so let's do that. So we have to write it as 1 over n cubed. And then we see that p is 3, and so again, that's bigger than 1, so we have convergence. All right, so that's just two examples. Let me erase them so that I can keep this two series up here a little bit. But what now, suppose we have something a little bit more complicated than that. So I'll start with the first example. Suppose our series looks like this. 1 over n squared plus 1. Okay, what do we have? Well, okay, if you think of it as n as a variable, it's clearly a polynomial in the denominator. But it's not the p series, because the p series would be 1 over n squared, right? Just on its own. That's the restriction of the p series, that's what it says, but it's not really that. So it looks like this, but it is not equal to that. And that is where the comparison series comes into, limit comparison. I'm going to do this example, but I'm actually going to start, it might be weird, with a more complicated example because it's easier for me to explain it that way. Okay, so here's the first of our example that I'm going to explain with. Suppose we have something like this, summation n, let's say from 1 to infinity. As I said, this never matters where we start from because everything is about how it ends here at infinity. Okay, so here's the one that I'm thinking of. I'm just making up something. 3n squared plus 4n plus 1 divided by 5n to the fifth plus 3n squared plus 1. Okay, so this is polynomials, so p polynomials, right? But it is definitely not the p series. It's much more complicated than just a simple p series. So what we will do here is follow here my steps. So remember, in general, we have a series like this, right? The ANs are the elements. So this is this would be my AN. Now, as the name says, comparison, I'm going to have to compare with something, and that one I'm going to call Bn. So I'm going to construct a new series. And what do I do? And this is, again, very particular to this test. We do something that we normally don't do, but here we're going to do this. So I'll use a different color. I'm going to look at the biggest power in the numerator. That is n squared. And I take that power. And then I'll do a different color. I look at the biggest power in the denominator, and that becomes my denominator. Okay, this is how I choose Bn. Right? I'll do more examples and it will clear what it is. But I hope what I do is the biggest in the top and the biggest in the bottom. Separately. I do each separately. I don't look at the biggest of everything. I look at the biggest of the top, that becomes the top. The biggest of the bottom becomes the bottom. Then, and this is important, I'm not simplified yet. Do not yet simplify. I'll say this because it's so you feel like, oh, I can simplify, let's do this. But this is what, as I said, we're doing something that we normally don't do. So this is what I call step 1. Now what is step 2? This is actually what we need to verify is we need to verify that the following thing, the limit for n going to infinity of an divided by bn. Okay, that's what we need to calculate, and the condition will be it should be not 0 or it should not be infinity. So we have to verify that this particular choice we made has this property. Okay, I'll write down later the full generality, what the limit comparison test says. Well, no, perhaps let me say this now. So this is what I'm going to do. I'm going to now verify this thing. So here is the actual limit comparison test in general, so that you can follow why am I doing what I'm doing. So we have a given series AN, and so we now we choose, and that's what I explained how to do this, and I'll give many more examples to show another series Bn, and I'm going to choose them in two things. Well, the first thing that I have to check is that the new series that I've chosen somehow has this property that if you look at the strange thing that we do, we divide an by bn's, and this should not be 0 or infinity. But that doesn't mean anything yet. The second thing that we have to do is then to check if this bn converge, then the an converge. This is the comparison that we want to do. So if we know what happens to Bn, then we know what happens to An. And in fact, I mean, this is true for convergence, but it's also true if it diverges, then An diverges. Okay? So whatever Bn does, also An does. And that is because the two are somehow related by this property here. I'm not going to explain why this is the case. You can look at the textbook, it's explained there a bit more. But that's what we need to do. Okay, so going back, I gave you a recipe of finding Bn. This is my Bn. So the next thing I have to check is this one, right? Alright, so let's do this. And again, the way that we do it is different than we normally do. So, what I'm going to do, I have to divide an, which is this fraction, by bn, which is this fraction. Now you say, oh, I see, you put one fraction on the top and the other in the bottom, and then the one in the bottom you flip over. I'm not going to do that. I'm going to calculate this limit in a very strange way, but you have to assure yourself this is correct. Okay, so what I'm going to do is, so I'll write it up here. I'll give myself a little bit of space because you see exactly what I'm doing. Okay, we start with an. An, the top of an is 3n squared plus 4n plus 1. And so that's my numerator of an. This is the numerator of bn, so I'm going to divide by that numerator. That's going to be on top. And in the bottom I do exactly the same thing. I take this denominator, 5n to the fifth, plus 3n squared plus 1, and then I divide by this denominator, the one from bn, and to the fifth. You follow this? Okay. So, what can I do now? Well, this is now equal to, let me make this a little bit smaller. Why do I do this? Because I'm going to simplify this fraction by dividing everything by n squared, which would be 3. Right? These two n squares cancel out. But be careful, it's not just that, right? I have to divide each term here. So we plus 4n divided by n squared, that would be 4 over n, plus 1 over n squared. We have done these things many times. Oh, this is still a limit, so I should write here, this is the limit for n going to infinity. What happens in the bottom? I do the exact same thing. N to the fifth divides each of these guys. Okay, so what we have, the first one is just 5. The second term, we have an n squared on top, n fifth on the bottom, so we actually have n cubed in the bottom, right? And then the last one is 1 over n to the fifth. Make sure that you understand where these powers come from. And now it's the usual thing with limits, right? It's the limit for n going to infinity, so each of these reciprocals go to 0. I remind you, 1 over infinity is 0. So if I plug infinity in each of these reciprocals, I get 0. So all these are 0, and so what I'm left with is 3/5. And it has to be different from 0 and infinity. Okay. Are we done? No. This tells us that, yes, the Bn you chose is a good choice. And now, remember what is this now tell? Now I'm going to think about this here. What about the Bn? Can we say whether they converge or diverge? Well, let's look. So step 3 is now looking back at Bn. I'm just copying. It's n squared over n fifth. Now I'm going to simplify. So only at this stage I simplify. If you simplify too early, then you're going to be stuck in this calculation here. It's not, I'm not saying it's impossible, it just gets harder to see what's going on. All right? Okay, so I now simplify, and remember what I'm going to get. Geometric or p-series? A p-series, obviously, right? So I'm going to write it as a p-series, and that would be in the denominator. Oh, okay, it's a p-series. So this is a p-series, and p is 3. So that means Bn converges. But if Bn converges, then An converges. So my conclusion is An converges. So this original sequence that I had is convergent. Okay. So perhaps a little explanation of why is this a correct way of putting fractions. Think about this. If you divide one fraction by another fraction, one valid way of doing that is dividing the numerators and dividing their denominators, and make that the new numerator and respective denominator. You can play around with this and you see that it actually is the same. Okay? So, quick review. If I have something that involves polynomials, like this, then I choose, make a Bn based on the choices that I just explained, highest power in top, highest power bottom. I then check that what I chose here satisfies this criterion here. Now, once we have this, which is our special way of calculating this, so once we get a number that is not 0 or infinity, we can now actually have a closer look at Bn. So now we look at this Bn and say that's what happens. Okay, let's do first another example. So please try this before you look at the sequel of my explanations. So 3n to the fifth plus 4n divided by 6n to the sixth plus 3n squared plus 1. Okay, I just took something. So step 1, choose Bn. What is Bn going to be? Well, I'll do it again. The highest power is n to the fifth. The highest power in the denominator is n to the sixth, so that will be Bn. But I'm not simplifying, because in step 2, what I need to do is show that the limit an divided by Bn. This is the limit I have to calculate. And how do I calculate this limit? Well, I take my numerator, 3n to the fifth plus 4n, divided by the numerator of Bn, and let's do the same with the denominators, 6n to the sixth plus 3n squared plus 1 divided by n to the sixth. And this is still a limit. Okay, so it's still a limit. I'm now going to divide everything. And remember, dividing means every single term. So I get a 3, with the n to the fifth cancel here. But here we have, of course, 4n to the fourth. Okay? And then, and the other one, I hope you see it, 6 plus 1, no, not 1, 3, that's the coefficient, right? N to the fourth plus 1 over n to the sixth. Okay? And then we use the fact that 1 over infinity is 0, so that this will go to 0, this will go to 0, and so will this. Therefore, what is left? Again, 3/6, I don't know how this came out. I like these numbers, I guess. 3/6, which is a half. Well, that's different from 0 infinity. That's the only thing that matters. Are we done? No, because we have to go to step 3. What does step 3 say? Inspect now what is Bn. Bn is, well, I'll write it, n to the fifth over n to the sixth. It's, again, a p series here. I'll do examples where you actually get the geometric series. And this time the power is 1, right? Remember, it's you bring this exponent down, so that it means subtracting exponent, 6 minus 5. Okay, what is p here? So it's a p series. What is p? P is 1. Is that good or is that bad? Well, if you forgot, look it up. P equals to 1 implies also divergent. So this is divergent. Oh, by the way, we had given a name to this guy. And I keep repeating this, we're going to use this a lot. So the harmonic series, right? That was exactly the p series where p was 1. Okay, so this means that this series is divergent. See? You can have either way. It depends just on whatever powers that you have. Okay. Here's another example that might say, oh no, what is this? Not the limit. So here is, what about this guy? No, what am I doing? N going from 1 to infinity. You're not going to like this, because I'm going to put in cube roots. N to the fifth plus 6n plus 1, say, divided by the fifth root of n to the 12th plus 4. Oh my god. No, not really. So, step 1. What is Bn? Well, let's think about it. What's the highest power? Well, the highest power is n to the fifth, but not really, because it's in the third root. So let's just write that. It's the third root of n to the fifth. That's what the highest power there is, right? Okay. And then the same for the bottom. It's the fifth root of n12. So it's the fifth root of n to the 12th. And your urge to simplify might kick in. Don't do that yet. Because the next thing I have to do, step 2, and that is why I want to write it this way, I have to calculate this limit. An over Bn, and An was this guy, so I do the same principle. I take the numerator, the whole numerator, n to the fifth plus 6n plus 1, and divide it by the numerator of my Bn. Okay, I hope you see where we're going with this. I do the same here for the denominator, so that is the fifth root of n to the power 12 plus 4 divided by this guy, the fifth root of n to the 12th. Okay, this is still a limit. All right, so what now? Let me put it underneath here. Well, what we now use is the fact that you can distribute a radical, not over a sum. So I cannot distribute this radical here over all these sum elements. That is not valid. But what I can do is over a fraction. So I can write this whole thing as the cube root of this fraction, n to the fifth plus 6n plus 1 divided by n to the fifth. That's a valid algebraic operation. And I do the same in the bottom. Now we have a fifth root. So we have n12 plus 4 divided by n12. And once these fractions are inside, you see we can do again what we did before, divide each numerator and denominator. So let me quickly do that. So that we get limit n going to infinity. The cube root, don't forget, there is a cube root, right? You have to keep writing that. So we divide everything by n to the fifth. The first one is 1, the second one is n to the fourth power, right? And then plus 1 n to the fifth power, all this inside. And then what do we have in the fifth root in the bottom? n12s cancel out, we get 1 plus n to, no, not n, 4 to divide by n to the 12th. And then finally, we use the fact that all these reciprocals will go to 0. So this is 0, this is 0, and this is 0. So our limit is 1 over 1. You cube root over 1 over the fifth root of 1. But whatever power of 1 you use, or roots or whatever, it's always 1. So the whole thing is just 1. Oh, 1. So that's the P series, so less than 1, so divergent. No. This is what we're doing. This one doesn't tell us anything yet. It just verifies whether you have the right Bn. In other words, is the next step, does it make sense to do the next step? And what is the next step? That's the one now where we will know what's going on. So now we have step 3 is we go back at what Bn is. So Bn, let's write down, it was the cube root of n to the fifth divided by the fifth root of n to the 12th. Okay, what about this guy? Well, these are powers, right? So let's write down what are these powers. This is, I hope everybody sees that it's the power 5 root 3 that becomes exponent 5/3. And in the bottom, therefore, that would be 12/5. Now we have to write it as a P series, which means in the denominator. So we're going to subtract. So we have 12/5 minus 5/3. Right? That's what happens if I bring that down. I subtract the exponent. Okay. Okay, what is that? I put that on common denominator. A little bit of work, but not that much. What's the common denominator? 15, right? So that's 36 over 15 minus 25 over 15. So what is that? So that is 1 over n. 36 minus 25 is 11 over 15. So P is 11 over 15. What about that? Well, that's less than 1. Scroll back up. What does it mean? Less than 1, unfortunately, means divergent. So this is divergent. So this is divergent, and so in conclusion, the original one, this is divergent. Okay. So, by the way, you might ask, okay, when you choose these, you choose the Bn, like here, look at this one. There was actually, the highest power was n to the fifth, but there was a coefficient 3 in front of it. I didn't take the coefficient. I could if I want to. There's nothing wrong with that. It's just not necessary. So why? Why? Because then you're going to create fractions. So keep it as simple as possible, just the powers themselves. Okay, now this is for the geometric series. Sorry, for the P series, right? Each time we compare with the P series, but there are examples where you can compare with the geometric series. Let's do that. So suppose we have to do this one. You see now that the n appears as an exponent. So we are dealing with an exponential function here, which means geometric series. Okay? And let me make it a little bit more complicated by putting here 15 something. Okay. We do the same thing. So step 1, what is b? Bn. We choose Bn, again the same. We're going to choose the highest. So okay, now highest degree. This is not degree anymore. So the better way to say is we choose this, we will choose the dominant term. So the dominant term, if you're dealing with powers, of course, is the highest power. So the dominant term of this guy would be 2 to the n, right? So that's the one that we put here. So let me do it still in my green here. So this one will become 2 to the n. Oh, no, I did this in another color. Okay, sorry. I'll keep my colors. So that's 2 to the n. And then what's the dominant term here? That's 3 to the n. I'll do another examples when there are several powers to decide what happens. Okay, 3 to the n. And next step is the same step as before. We have to calculate a certain limit, namely the limit for n going to infinity, an over bn, and we do exactly the same. We take the original numerator, 2 to the n plus 15, and divide by the one from bn, and do the same for this guy. So 3n plus 4 divided by 3n. And now we simplify. We actually carry out the division in top and bottom. Remember, but dividing is each single term again. So the 2n with the 2n cancels and get 1. But what happens there? Well, we have 15 divided by 2 to the n. Let's write it like that. There's no need to write it differently. And the same with the bottom. We have a 1 here plus 4 over 3 to the n. Now what's the deal here? Of course, if I put an infinity in this guy here, if I'm putting infinity here, I get 15 over, so I'm putting infinity, so n equals infinity. What do we get? 15 over infinity, 2 to the infinity is infinity, so that's 0, right? So again, exactly the same thing. This is going to be 0, and this is going to be 0, so the answer is 1. What does this mean? Nothing. What we wanted to see is whether it was 0 infinity. And if you choose an, bn correctly, it will always come out the way it should be. But you have to show me, okay? Don't skip this step. You have to calculate this limit. I need to see that you understand how these limits work. All right. So, but are we done? No, as I said, we still have the step 3. Now we're going to take a closer look at Bn. What is Bn? In this case, it was 2 to the n divided by 3 to the n. Oh, you say that's not a geometric series. What is this now? Okay, there are 2 geometric series. Well, remember, I did this example all the way in the beginning. I think I erased it, right? Do I still have it? Yeah, no, I erased it. Okay, so what you do is you combine it as one single power. So this is 2/3 to the power n. And now it looks like a geometric series, right? In a geometric series, we have this r to the power n. There's no a here. The a is not important here. So r here is 2/3, which is less than 1. Be careful. In the geometric series, that's a good thing. So this means convergent. Okay, again, if you don't believe me, where is it? Here, right? We are in this situation. Okay. So what is the conclusion? Convergent. The Bn is convergent, therefore the original one was convergent. That's my conclusion now. I'll do another one, and that's the only thing that we need to do, and then for the rest I'll give you some homework problems. I'll again assign them, I'll put them on the web page. So here is the thing, another example, slightly more complicated. Again, we go from 1 to infinity, doesn't matter, so I'm just going to be 1. 2 to the power n plus 4 to the power n divided by 5 to the power n plus 2 to the power n plus 1. Okay, so step 1, what is Bn, right? You notice that all are powers. By the way, if you would have a mix of, they're all are exponential functions. If you would have a mix of exponential functions and power functions, this doesn't work. There are ways that you could make it work, but again, you will never get a problem in that. So for us, it's either compare it with the p-series, like when it looks like something like this, involving possibly radicals, but polynomials and radicals, or something like this involving only exponential functions. So what is Bn? Again, we choose the highest. The dominant, right? So remember, dominant. What does dominant now mean? Well, there are two terms, and they're both exponential functions. What do you think is the dominant? The one that is the highest base, the biggest base. So this is the dominant, right? The dominant doesn't necessarily be the first one, right? So be always careful. We sometimes write it in first, but it doesn't mean that it has to be. So 4 to the n is my dominant term, and the dominant term in the bottom, I hope everybody sees it, this time it's 5 to the n, because that here with base 5 is bigger than base 2, and of course this is just a constant. So okay, 5 to the n. All right, that's not the end of the business. Step 2 is something we have to do. We have to calculate this limit. And you'll see it's a little bit trickier here. So pay attention here. I get what we do as before. We have space enough. 2 to the n plus 4 to the n. Take the numerator of an and divide it by the newly chosen numerator. And we do the same with the denominator. So we have 5 to the n plus 2 to the n plus 1 divided by 5 to the n. Okay, we carry out the division. We have 2 to the n divided by 4 to the n. Let me still write it this way. And then 4 to the n divided by 4 to the n, that just gives me 1. That's easy. And then there we have a 1 here the first time. The second term is 2 to the n over 5 to the n. And the third term is 1 over 5 to the n. Okay, now 1 I see already immediately. This, if I plug in infinity, this is going to 0. But what happens if I plug in infinity in here? Let's work it out a little bit. If I plug in infinity, I get infinity over infinity. Oh, you say, I know, L'Hopital. Good luck with that. Because if you do L'Hopital, you'll see you basically get the same thing. You're not going to get anywhere. So how do we figure out what the limit is? Think a bit about it. It's actually something we've done already, not for limits. But remember, here, if you have a fraction of 2 powers, exponentials, you can write it as a single exponential. So let's do that. So, okay. So I'm going to rewrite this. I'll write it now here, the whole thing. So I'm going to rewrite my 2 to the n over 4n just as 2 divided by 4 to the power n plus 1 divided by 1 plus, and I will do the same with this guy. So 2 over 5 to the power n plus, well, okay, 1, 5, and let me write it now. And so what happens now? Okay, 2 to the 4, well, 2 to the 4 is of course a half. But what we have to think about two things. We have exponential growth. These are exponential functions that look like this. That's a to the n. And here, if the base is bigger than 1, that's exponential growth. What is exponential decay? This is something from a long time ago, right? So exponential decay, the exponential function now looks like this. So that is a to the n, and this is for a less than 1. So it depends on whether the base is bigger or less than 1. So here we have, in both cases, this base is a half, which is less than 1. So we're dealing with exponential decay. So in the limit, we will have 0. So that's why we can say that this limit is equal to, well, this is 0 plus 1. This is the 1 here. Plus, now this guy, again, has a base that is smaller than 1. And therefore, this would give me 0 again. And we already argued that was simply also 0. And therefore, the answer is 1, which is, what matters is it's not 0, it is not infinity. So that's good, right? That's the condition here, where let me go back to the... So we have now verified that this is true, and now we can go to that. So if you want, this you have to do first, and then second. Right? You have to first verify that that this limit is not zeroing infinity, and then secondly you look at Bn. Okay, let's look at Bn now. Bn, I'll copy it from here. Where was Bn? 4 to the n over 5 to the n. 4 to the n over 5 to n. I hope by now you know what to do. You combine them as one single exponential with base 4/5, and then you see that r is 4/5, which is less than 1, so we have convergence. Yay. Okay. Okay, so I'm going to assign homework problems for this, and then these homeworks are going to be due, oh dear, next session. Okay, our schedule is going to be a little bit confusing because we have now, we skipped the Tuesday because this was, we broke our spring break in 2 parts, basically. That's what's happening. So the next session I will post when the next session is, and the homeworks for this will be due then. But okay, and please, although we have also a quiz today, I know this preoccupies you always, but after you watch this thing, leave a comment. Don't forget to do this.